All right, so to introduce the idea of probabilities and how to work with the concept of and with probabilities and the concept of or with probabilities, we're going to deal with a simple deck of cards. So a typical deck of cards has 4 suits, diamonds, hearts, clubs, and spades. And it has an ace, which stands in for a 1, the numbers 2 through 10, and then a jack, queen, and a king. So if you count that up, 1, 2, 3, 4, 5, 10, up for the numbers, plus jack, a queen, and a king is 13 different cards in each suit. So 13 times 4 is 52 cards in a standard deck. We're going to leave jokers out because that just complicates things. So to start off, I want to know the probability of getting a club, or more appropriately known as the suit of destiny. So if we were to do a probability of getting a club, I would write that this way. The probability of getting clubs is... Now when you do a basic probability, all you're doing is counting the number of ways that happen like this out of the number of ways it could turn up in general. So if you think about clubs, in a standard deck there are 13 clubs, ace through king, and there are 52 cards in a standard deck. So the probability of getting a club should be 13 out of 52. That means that if you took a random deck, shuffled her up, and then cut the cards, and you just kept doing that over and over and over and over again, 13 out of every 52 card cuts should be clubs. Now if you're good with fractions, you might notice that 52 happens to divide by 13, and that reduces to 1 out of 4. Which isn't a surprise, because if you picked an 8, for example, it's either the 8 of hearts, the 8 of diamonds, the 8 of spades, or the 8 of clubs. Only one of those is a club, 1 out of 4. So it's not a coincidence that those two fractions happen to equal each other. Now the next one here, getting a non-face card. Now we could get into a fight whether an ace counts as a face card or not, and if you say that it is, you're wrong. Because you will not find a face on an ace card. So if we go and look, the probability of not a face this is the good part about being the person making the videos. I can make these broad and outrageous claims that an ace is not a face card, and there's nothing you can do about it. So there. So not a face card. So there's the ace, the 2, the 3, the 4, the 5, all the way up to 10. So there are 10 cards that in hearts that are not face cards, and there are 10 diamonds that are not face cards, and there are 10 clubs that are not face cards, and 10 spades that are not face cards, for a total of 40 out of 52 cards. Now both of those numbers divide by 4 as well. That's going to give 10 out of 13. Now that's the number we had out of each suit. 10 cards, the ace through 10, out of the ace through king are not face cards. So we have that. Excellent. So now that we've got that established, I would like to talk about the probability of getting a card that is a club and not a face card. So if I were to write that in my notation here, that would be the probability of a club. The word for and is the intersection symbol. And not a face. Now, I want to think about that. So the cards that are both clubs and not a face club are the ace of clubs, 2 of clubs, 3 of clubs, 4, 5, 6, 7, 8, 9, and 10 of clubs. That's 10 cards out of the standard deck. 10 out of 52. Now that fraction happens to reduce both of these numbers cut in half. That would be 5 out of 26. Now that's fine for something that we know about, something that you can take. You can take a deck of cards and spread them out on the table, and you can count the things that meet both of these criteria. But the real advantage of probabilities, and when you're dealing with statistics in particular, is that if you know the probability of one thing and the probability of another thing, you should be able to calculate the probability of something being both of those quantities. And it doesn't have to be things about suits and face cards. If you knew the probability of someone making more than $100,000 a year and the probability of somebody being born in Bruce County, then you should be able to go through and calculate the number of people who make more than $100,000 and were born in Bruce County based on these numbers. So we're going to just try a calculation and see how it goes. So the way the theory works is that if, and let me underscore this word, A and B are independent events, then the probability of A and B is the probability of A happening multiplied by the probability of B happening. Now that's real general and maybe a little difficult to wrap your brain around. This phrase up here, independent events, means that the two things have nothing to do with each other. So an example of something that might not have anything to do with each other is the probability of being more than 6 feet tall and the probability of liking blue as your favorite color. One assumes, hopefully correctly, that your height above the ground doesn't affect your preference for the color blue. So I should be able to find the probability of 6-footers who like blue by taking the probability of being over 6 feet and multiplying it by the probability of liking blue. An example of something that is not independent would be something like the probability of getting in a car crash and the probability of surviving a car crash. Because you can't have survived a car crash without having been in one. Those two things aren't independent. So when you're doing this particular calculation, you have to ask yourself, are these events unrelated? And if they are, you're good to go. The flip side of that, which is maybe the more interesting one, is that if you do this calculation and the observed probability and your theoretical calculated probability, if they don't match, then that's a sign that two things are in fact connected somehow, even if you don't think they should be. But we're going to get to that shortly. So we're going to try this out with this idea of being a club and not a face card, because we already have an answer for that. So if I were to try and use this formula then, the probability of being a club and not a face should be the probability of getting a club and the probability of it not being a face card. Alright, now the probability of being a club was 1 out of 4. And the probability of not being a face card was 10 out of 13. Now, if you multiply those two things together, because you have excellent fraction skills, Numerator times numerator would be 10. And 4 times 13 would be 52. Now, that fraction should be familiar to you because we already wrote it down here. And we got this one by actually laying the cards out on the table and counting which ones actually met those criteria out of the total deck. So, hooray for us. We've just shown that that happens to be true. So, trying to do the probability of a card that is a club or a face card, if you start thinking about that, in our notation, the probability of a club, the symbol for or is the union, or non-face. You think back to the Venn diagram on the other side, that would include all the cards that are clubs. So that's 13 of them. There's 13 clubs in there. And I have to add to that all of the non-face cards that are not clubs. So there's 10 hearts, 10 diamonds, 10 spades. That's 30 cards. Plus the 13 clubs should give me 43 cards out of the 52 that are either clubs or non-face cards. So if I were to try and write this, the probability of A or B, I'm going to start a formula here, and it's going to be wrong. So then we're going to add to it in a second. When I did A and B, I just took the probability of A and added it, or multiplied it to probability of B. This one, I'd like to add them. Probability of A plus the probability of B. And maybe you'll see why this doesn't work in just a second. So in this example here, the probability of it being a club or a non-face card or non-face would be the probability of a club plus the probability of non-face. Well, the probability of getting a club was 1 out of 4, and the probability of a non-face was 10 out of 13. Now, we could do this with fractions. I'm going to flip to decimals just so no one has a heart attack. So 1 out of 4 is 0.25, and 10 out of 13 is 0.769. And if I add those, I get 1.109, or 1.019. That's a 101.9% chance. So round that just for fun. That's a 102% chance. That's wrong. If I were to hand you a deck of cards and say, pick one at random, what's the probability that the card you pick is a club or a non-face card? Well, there's two issues with that. First off, you can't have a 102% chance. It's either 100% or that's it. You can't get an extra card or be extra more than 100% sure it's going to happen. That's not a thing. Unless you're giving 110% in data management, and then that's a good idea. Anyway, so that's the first problem. This number can't add up to more than 100. The second issue is that you might reach into that deck of cards and pull the King of Hearts. Well, the King of Hearts isn't a club, and it's a face card. And I already said there was a more than 100% chance of that not happening. So this is all inconsistent. The problem is that we've overcounted. And how did we manage to do that? Well, the probability of a card being a club included the ace through 10 of clubs. The probability of being a non-face card also included the ace through 10 of clubs. So those cards were counted in this pile, and they were counted in this pile. Just like the letters that happen to land in both exaggeration and quasimorphism, there are some that land in both sets. So if you just add them together, then you end up double counting a number of your data points. So I have to correct that here. The issue was that some things fall into this and this. So in order to make the calculation work, I have to remember to take out my double counting of the ones that are in A and B. So if I were to do that, minus the probability of them being clubs and non-face, see, what was the probability of them being a club and a non-face card? Well, I think we calculated that as being a club and a non-face card was 10 out of 52. Which was 5 out of 26. Gross. Now I could subtract that out as a decimal. .192 if I do some rounding. And if I try that again, 0.25, so that's the probability of being a club, plus the probability of being a non-face card, minus the probability of being both, I end up with 0.827. That's an 82.7% chance. Okay, great. When I looked over here in the last example, I happened to find my answer just sitting casually waiting for us to discover it. And so we're going to check this then. What is 43 out of 52? If I do that, 43 divided by 52, I end up with 0.827 if I round. So by adding this little correction in here, where I take out the double counting of things that are both this and that, I'm able to calculate these probabilities for independent events. All right, so to bring all of this together, I have a little survey here done on 68 graduating students. They were asked if they had an average over 80%, if they participated in extracurricular activities, or if they rode the bus to school. So 36 said they had an average over 80, 22 in extracurricular, 43 in total rode the bus. Of those, 14 had over 80 and participated in extracurricular, 23 had over 80 and took the bus, and 11 took the bus and did an extracurricular activity, and 5 people claimed to do all 3. Now, we're going to draw a Venn diagram to sort of sort these people out, and the plan is to eventually check to see if these 3 questions are independent of each other. Does taking the bus affect your ability to get 80% or more in your average? So we're going to start with our Venn diagram. So there's 3 questions, so I'm going to need 3 categories. So we have 80%, we have the bus, and we have extracurricular. So first off, 5 people out of these 68 claim to do all 3. So the place in this diagram where they go is right in the center, where all 3 criteria meet. Now, this next one up here, 11 took the bus and did extracurricular. So that's this section here. right, where bus and extracurricular overlap. But you notice that I already have 5 people in there. So some of these kids who took the bus and did extracurricular also got over 80, but they're included in this 5 here. So I would be double counting them if I put 11 in this section. So instead of putting 11 here, I need to make sure there's 11 in the whole overlap. If I already have 5 accounted for, that means that there are 6 who are not. 23 had over 80 and took the bus. Over 80 and took the bus. That's here. So there need to be 23 people in this section. 5 of them are already accounted for. That leaves 18 that are not. So I'll get them in there. 14 had over 80 and took or did extracurricular activities. So that's here. 5 of them are already accounted for, leaving 9 behind. Now if 43 people rode the bus, that's 43 people in this particular section here. But again, you can see that there are some of them have already been sorted, and we can't be double counting them. So if I take those 43 people who claim to ride the bus, and I take out the people who rode the bus and got 80%, so take those 18 out. And if I take out the 6 who rode the bus and did extracurriculars, and I take out the 5 that did all 3, I end up with 14 people unaccounted for. If 22 participated in extracurricular, that's down here. So of those 22, I have to take out the 9 who did extracurriculars and 80%. I have to take out the 6 who did extracurricular and rode the bus. And I have to take out the 5 that did all 3, leaving only 2 people behind. And if 36 had an average over 80, take those people and remove the 18 who also took the bus, remove the 9 who also did extracurricular, and remove the 5 who did all 3. I end up with only 4 people. Lovely. So what I have here are some probabilities, or some sorting then, of all these people in there so that no one is double counted. And so what I'm going to do then is I'm going to make a chart that's going to compare the theoretical probability with the observed probability so that I can see if what I'm finding probability-wise matches what I would calculate. And if they do, right, if the probability of A times B equals the probability of A and B, then I've shown that those two things are independent of each other. So in my chart then, I'm going to have some combinations. So I'm going to do 80s, and bus. Now, observed, the people who got an 80 and took the bus are here. That's 23 out of the 68 people. So I'm going to jot that in there. 23 out of 68. Now, theoretically, I should be able to arrive at that same probability by taking the probability of getting an 80 or more and multiplying it by the probability of taking the bus. So the probability of getting an 80 or more would be 36 out of 68. And the probability of taking the bus is 43 out of 68. And I'm going to multiply those two things together. So 23 out of 68 is 0.3382. 36 out of 68 multiplied by 43 out of 68 gives me, not that, 36 out of 68 times 43 out of 68 equals 0.3348. So I was expecting there to be a 33.48% chance that a person took the bus and got an 80. And then I actually went out and sampled them, and I found that 33.82% of people got an 80 and took the bus. So the fact that these two things match, not exactly, but they're very close, suggests that they are independent. So my study here has led me to the conclusion that riding the bus doesn't prevent you nor encourage you from getting an 80% or more on your average. Next one we're going to check is getting over an 80 and participating in extracurricular. So the observed probability for that, getting an 80 and extracurricular, is here. Is these 14 people out of 68. Now 14 out of 68 is 0.2059. Now, in theory, I should be able to take the probability of getting an 80, which is 36 out of 68, multiply it by the probability of being an extracurricular, which is 22 out of 68. And if these two things are independent of each other, so they have no effect on one another, then the answer I get here should match the answer I got there. So let's give that a try. 36 divided by 68 times 22 out of 68 gives me 0.1713. Now, those don't match. This is almost 21 if I did rounding, and this is only 17. So I found, when I looked, there were 4 percentage points more showing up in this category than what is theoretically expected. So these two things, there's evidence here that they are not independent. In fact, because the observed probability is higher than the theoretical probability, there is evidence here to suggest that these two things encourage each other. Either getting an 80% average encourages you to participate in extracurricular activities, or participating in extracurricular activities encourages you to get an 80% or more. Or that the people who are inclined to being in extracurriculars are also people who are inclined to getting an 80 or more. I don't have enough information to nail down why, but I do have some evidence to suggest that there is a relationship between these two things, getting an 80 and participating in extracurricular activities. So if I were studying this for real, then I would be encouraged to go and do more research in that particular direction to see what it is exactly causing that relationship. So just to finish, they're not independent. In fact, it's overrepresented. All right, now there's only one more combination to do, and that is taking the bus and being an extracurricular. So, observed, taking the bus and extracurricular, where is that? That's here. That's 11 people out of 68, which ends up being 0.1618 if you round. And theoretically, I should be able to take the probability of being on the bus, that's 43 out of 68, and participating in extracurricular, which is 22 out of 68. Let's see what that gives us. 43 out of 68 times 22 out of 68 gives us 0.2046. So that's a 16%. Only 16% of people were observed to do bus and extracurricular. And in theory, there should be almost 21. A little more than 20, a little less than 21. So these two things are not independent because those percentages don't match. In fact, the observed is underrepresented compared to what should be there theoretically. So again, I don't have any evidence that says why. I only have evidence that says that these two things are mismatched. So maybe taking a bus discourages you from taking extracurriculars. Maybe being in extracurriculars discourages you from taking the bus. Maybe people who don't like buses also don't like soccer. I don't know. I don't have that information, but I do have some evidence that these two things are not independent. And in fact, they're underrepresented.